Hello. Let's talk more about sentences with more than one quantifier. In our previous lesson, we encountered a modified definition of a substitution instance. Now we're going to practice how to get substitution instances. This is a skill that is very important for evaluating the truth of quantified sentences, and therefore for determining whether they are logically true or contradictory, and whether the arguments in which they occur are valid. So, how do you get substitution instances when you have more than one quantifier? Let's see if we can provide a series of steps. So suppose that I tell you, give a substitution instance for 1 using A as a name. So let's put it to the one side. And so here are the steps. The first one is to eliminate the leftmost quantifier. And so we're left with this. There is a y, rxy. And notice that this is an open sentence, because the occurrence of x has been left free. And so we take each free occurrence of the quantifier's associated variable, which in this case it is x, and then we replace it with a. And this is what we have. There is a y such that ray. And indeed, there is a y ray is an a for x substitution instance of every x is such that there is a y rxy. So suppose that I want to do it again. Suppose I take this sentence that we arrived at and I want a substitution instance of this in its turn. And so I tell you, give a substitution instance of 2 using b as a name. And so we follow exactly the same steps. We eliminate the leftmost quantifier and we are left with this sentence, which is open because y occurs free after we eliminated the quantifier. So we take each free occurrence of y, and then we substitute it with b. And we end up with this, RAB. And again, RAB is a b for y substitution instance of there is a y ray. And this is how you proceed methodically. First, you eliminate the leftmost quantifier, and then you replace each free occurrence of the variable that accompanies the quantifier you just eliminated with the name that you chose. And here we're basically following the definition that we gave in our last lesson. So let's see some of the applications. How does this apply to truth in an interpretation? Well, suppose that we have an interpretation and we have a sentence that we can ask, is 1 true in interpretation I? Well, remember that y is a universal sentence. So it is true in I just in case all of the substitution instances are true in I. So we have to get all of the substitution instances of sentence 1. So it has 2 substitution instances since there are 2 names in the domain. So these are the 2 substitution instances. One is obtained by substituting a for x. The other one is obtained by substituting b for x. Okay, now we have to evaluate each of the substitution instances to see if they are true. Is the leftmost substitution instance, the one in which we substituted with a, is it true? This is an existentially quantified sentence. So it is true if and only if at least one of its own substitution instances is true. And this also, again, has 2 substitution instances. One when we substitute y with a, and another one in which we substituted with b. Okay, are they true or false? Well, the answers are in the chart to the left. RAA is true, and RAB is false. So we can see that at least one of its substitution instances is true, namely RAA. That's what makes it true. So the existential sentence itself is true in I. So the first substitution instance is true. What about the second? Well, again, it has 2 substitution instances, RBA and RBB. And if we look at the chart, we see that the first one is false, but the second one is true. So there is at least one instance that is true. Therefore, the existential sentence is itself true. So we can see that all of the substitution instances of this universal sentence at the top are true in I. Therefore, for every x, there is a y rxy is itself true in I. The next application is to invalidity. So suppose that you have this argument, and the premise is everybody loathes someone, which we represent as for every x, there is a y, lxy. And now the conclusion is, therefore, there is someone in particular whom everyone loathes. and which you represent as there is an x such that for every y, all yx. Well, clearly this argument is invalid. To show that this argument is invalid, we must come up with a counterexample. In predicate logic, a counterexample to an argument is an interpretation that makes its premises true and its conclusion false. So let's try to come up with one. The situation described in the premise is this. Every domain member loathes at least one person, someone else or themselves, doesn't matter. However, the conclusion says something stronger, namely that some specific individual is the object of universal loathing. A scenario in which the premise is true and the conclusion is false is one in which everyone has someone, one or more, they loathe, but where there is no single individual that is loathed by all. Something like this. Suppose that Al loathes Claire. Suppose that Al loathes Beth. And suppose that Claire loathes herself. So, although everybody loathes someone, there's no one in particular whom everybody loathes. Now let's do this with the methods of predicate logic. Here we're going to show that this interpretation is a counterexample to the validity of the argument. Remember that in a counterexample, the premises must be true and the conclusion must be false. We only have one premise, so the first step is to make that premise true. And the premise is a universally quantified sentence. And this sentence is true if all of its substitution instances are true in I. So there are two substitution instances. And again, this domain is different from our previous example. Here we have just two people. And so the two substitution instances are, there is a y, lay, and there is a y, lby. And so are they true? Let's begin with the first one. This has two substitution instances, laa and lab. And the first one is true and the second one is false. So we see that this substitution instance is true because, again, one of its own substitution instances is true. Okay, so the first substitution instance of our universal is true. What about the second? Its own substitution instances are lba and lbb. The first one is false, the second one is true, and that makes the existential true because at least one of its substitution instances is true. So we can see that all of the substitution instances of every x, there's a y, lxy are true. Therefore, this sentence is true in I. So our premise is true. Now let's show that the conclusion is false. So this is an existential sentence. There is an x for every y, lyx. So it's going to be true if at least one of its substitution instances is true in I and false otherwise. This sentence has two substitution instances, which in this case are universal. So the first one is every y, lya, and this has two substitution instances, laa, lba. And remember that this is going to be true if and only if both of those substitution instances are true and false otherwise. So we look at our table and the first one is true and the second one is false. So that means that our universal is going to be false because the second one, lba, makes it false. What about the second one? Every y, lyb. It has two substitution instances. And, well, we can stop at the first substitution instance. We know that it's false, therefore not all of its substitution instances are true. So the second is also false. So we see that not even one of the substitution instances of this existential sentence is true. So all of the substitution instances of there is an x for all y, lyx are false in I. So this means that the sentence is false in I. But this sentence was our conclusion. So we have shown then that in this interpretation, the premise is true and the conclusion is false. So this interpretation is a counterexample to the validity of this argument. This argument is invalid. Okay, goodbye.